Ooh.
Bless you. Bless you.
I don't know why the planet wants to kill me, but it has plans to kill me. And the cedar trees are first in line.
Oh yeah, they're better this time of year.
Cedar. Did not know I was allergic to cedar until I moved to a place called Cedar Park.
Everybody always says that. They're like, you never know if you have allergies until you move to Austin.
Yeah.
Like, then you'll find out.
All right, we are going to keep moving inexorably across the periodic table, really looking at the top important elements right here. See what we've got. And we're in group 6. Get a little bit about phosphorus. Oh, we're going to do nitrogen. So we're still in group 5. Group 5. Of course, group 5 to us
15.
is group 15. For reasons that haven't been explained yet, but they will, because our 8 electron rule is now going to be an 18 electron rule. It will all make sense eventually. All right, let's start then. We've got to look at nitrogen. Nitrogen, of course, occurs naturally as N2, which we demark as dinitrogen so that the people who we're talking to don't think we're talking about atoms, we're actually talking about molecules. We've seen its Lewis structure, we've seen its Kepler structure, we've seen its molecular orbital energy diagram, and it has a triple bond, which means that its bond enthalpy is 940 kilojoules per mole. And that's in the endothermic way. So that molecule is incredibly difficult to break. And one of the things that we say to the students in general chemistry is if I had to break a bond between A and B, that bond is a single bond versus a double bond. If you were dangling off a cliff, would you rather dangle by one hand or two hands? Okay? Because in the event that I find enough force or energy to stop you from dangling, then you plummet. However, if I chip away at this one, and I've found enough force or energy to break that bond, now I'm going to start working on this other one. Well, you've never really moved very far. So while I'm working on breaking this one, you're dangling from the cliff by both hands and I'm stamping on your feet. You can go pow, 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 pow for a second, but then put your hand back up. Well, if you're dangling off a cliff, would you rather dangle by one hand or three hands? This is difficult to get hold of. And it's worse, or better, depending on what your opinion is, because now there's not even a dipole. So this molecule, nitrogen, ends up being 78% of the atmosphere because it has that really super high bond enthalpy. which we can explain away because there's 3 of them. And it's non-polar. So there are things in the world that are non-polar. And then there's a slight step beyond polar, or non-polar, that is polarizable. Okay? So if I had this molecule, carbon tetrachloride, tetrachloromethane, is that molecule polar? It's a tetrahedron. Tetrahedron's a geometric shape in which all of the angles are the same and all of the distances are the same. And all of those bonds are polar out to chlorines equally. So there is no polarity associated with this molecule. But this molecule is polarizable, meaning if I bring something big full of electrons towards this molecule here, then the electrons that are in that chlorine, the chlorine is much bigger than carbon, might just move. And so I end up with the back end of the molecule. The electrons just push. And this back end gets to be a tiny bit negative, just because it's moving away. The big, soft elements on the periodic table are polarizable. Nitrogen isn't, it's small. One of the things that we're going to talk about eventually is there's a notation that we're going to start to call atoms hard or soft. And it's not literally, is this a hard atom or is it a soft atom? But when we look at its electron cloud, is that electron cloud a big diffuse cloud, or is it held tightly in a small shell? Hard versus soft. There's going to be hard versus soft acids, and hard bases, and hard and soft bases later. It's non-polarizable. So I can't get a handle on it because both ends of that molecule are the same. When we did when we looked at its molecular orbital diagram, the atom in the middle, and the atomic orbitals on the outside. Nitrogen is 1, 2, 3, 1, 2, 3. There's 1, 2, 3, 4, 5, 6. So I get that triple bond. That's lots of energy pulled in tight right there to make a really good triple bond. This molecule is non-polar and non-polarizable, and it also turns out that that gap between our highest occupied molecular orbital and the lowest unoccupied molecular orbital is big. And what that does is it means that there's not even something accessible nice and easily that allows electron transfer. Once we start to have electron transfer in our molecules, we can do oxidations and all sorts of stuff like that. But that gap is big, and it prevents electron transfer. And the loss of electrons is oxidation, and so we don't get easy oxidation of dinitrogen. Now, dinitrogen in the atmosphere can be oxidized have a think. What can happen to the N2 that is floating around in the atmosphere that will make it react? So all of these things combine to make dinitrogen an inert gas. And the fact that it's inert and stable means that it gets to be 78% of the atmosphere, or 50% of the atmosphere. What event, naturally occurring, could cause the nitrogen that's in the atmosphere to be oxidized? Because remember, 20% of the atmosphere is oxygen. So I've got a mixture of oxygen and nitrogen in the sky, and neither of them really want to react, especially the nitrogen. It does not want to react. What natural thing forces nitrogen and oxygen to react together? Lightning. Lightning presents enough energy to bond nitrogens and oxygens together, and then we get nitrates and nitrogen oxides. There's a lot of different types of nitrogen oxide. And we'll talk about nitrogen oxides in a minute. If I could get through the lecture. This lecture being brought to you by Clarity. All right, let's run through some ions. There's a lot to talk about in terms of oxides, a lot more than you would think. I think pretty much for general chemistry, you've been presented with nitrate, and that's mostly done as, we do know that there's a thing called nitrite, and we get to use it a tiny bit, but there's a lot more out there. So let's look at nitrogen's ions. It has two ions that are not oxoanions, not in combination with anything else. And they are nitrides and azides. And a nitride is an N3 minus. Okay, so we look at where nitrogen is on the periodic table. It's on the right-hand side of the periodic table, which means it's a non-metal. It will undergo reduction. And so we see nitrogen plus 3 electrons, gain of 3 electrons, makes me N3 minus. That technically occurs in 3 steps. Each of those steps is an electron affinity. I don't think I have anything at all to say about the magnitudes of those electron affinities. I didn't look them up. I don't know that there's anything profound in there. Electron affinity occurs in 3 steps, which your EA1 is N plus an electron, makes N minus. EA2 makes N minus plus E, makes N2 minus. And then your third one, N2 minus plus an E, makes N3 minus. So I did not look these numbers up, but there are things that we know because we have brains and we can figure it out. It does a nitrogen no good. Oh, I started the wrong side. Oh, it's still wet. One entire day later, it's still wet. Nitrogen starts out as 1s2, 2s2, 2p3. If it gains an electron and becomes N minus, it's 2p4. So it went from having 5 valence electrons to 6 valence electrons. Is that cause for celebration? No. There's no 6 electron rule. There's an 8 electron rule. So I'm only happy, I better write it here. I'm only happy right there. I have 8 valence electrons at the nitride, the N3 minus, so I know that there has to be an opening to allow this to happen. This must be accessible to us. Otherwise, it just wouldn't happen. If the energy wasn't there in these 3 individual processes, then it wouldn't happen at all, and we know it does. But of these 3, which one's going to have the highest value? Which one's going to be harder to achieve? The exact opposite of this question was on exam 1, which you can get back today. Finally. Exam 1 had a question that said, why is the second ionization energy double that of the first ionization energy for whatever ion we're working at, magnesium, I think. I think it was magnesium. Because making Mg1 plus makes no sense to us, but making an Mg2 plus does, because I could lose both of my electrons and have a closed shell. So why is it that the second loss of an electron was so difficult to do? That's my first ionization energy. My second ionization energy is this. So this is the exact opposite. Although magnesium ends up here, when I look at these 2 energies, this one was more difficult to do than the first one. Why? Because electrons are negative, and to pull an electron away from an uncharged atom takes a certain amount of effort. But to pull a negative electron away from a positively charged ion is now more difficult. So when we look at electron affinities, we should, although all 3 of these together is going to be achievable, we should be able to see that sticking electrons into something that's already negatively charged should be more difficult than sticking them into something that isn't. Got it? Okay. No numbers. Don't need to know sequence. Okay, so we make nitrides. Let's see if they're useful. 3 different types of nitride. Nitrides can be saline nitrides. These are just the regular ones. They're regular, ionic, and you make these with group 1 and 2 metals. So the lithium, top of the group, that is what we would call a saline nitride. Just did this in general chemistry, had them balance this. Nitrogen, of course, comes to you delivered as N2, and so I only have one nitrogen here. I'm going to need two, because I have two of these, which means I need 2 times 3, 6. Say these are ionic. Depends which metal you pick. There is some covalent character in some of the saline nitrides, depending on were you at the bottom of the group, where the most regular metal behavior is, or are you at the top of the group where there's more likely to be covalent character? Okay. Saline, something covalent, and then interstitial. Covalent. All right, if you find something that is non-metal, they make nitrides. What would be a good candidate for a non-metal to react with N3 minus?
Would you ask this all the time?
I know that my anion is N3 minus. What would be a good candidate to make a covalent nitride on the periodic table? Pick an atom on the periodic table that you think would be good at doing this. No. Let's be a non-metal. Pick a non-metal.
Oxygen. No. Carbon.
Okay. There is a thing called cyanogen, which is a carbon nitride. But wouldn't it just make more sense to do something from group 3?
Yeah. Like phosphorus. Yeah. No.
Okay. Phosphorus isn't in group 3.
Oh, group 3. I was
So
looking
now
at group 5.
group 3, now group 13.
I was looking at group 15. My bad.
Boron and nitrogen just click together and you make boronitrides. And then sulfur, so you could do it with, you can do it with oxygen, but we're going to reserve looking at that for when we see oxygen later. There is an S4N4. Don't think we're going to come back to the boronitrides. If we were going to see them, we would have seen them already. And then there's a whole bunch of these other types. They're called interstitial. You know what interstitial means? We've said it. Said it a couple of times. What is an what are interstices? You have the gaps, an interstitial site, or interstices of the gaps. So we're going to have a metal that metal could be cubic or hexagonal close packed. And then the N3 minus sits in the interstices, gaps. And we want them to be the octahedral ones. We set the octahedral interstices. And these things end up being hard materials. And quite lustrous. So shiny, big shiny objects. All right, the other ion of nitrogen that does not have a second atom in it, so it's not a oxoanion, is azide. And azides are toxic. What do you use azides for? They have more stuff going for them than being toxic. But being toxic is one of the reasons that we use them. None of you own a house? Not yet? Any of you do your own yard work? You ever use fertilizer? No? You ever use the fertilizer with the weed killer in it? Wait, she said no to the first question, so I'm just going to say no to the second one. Azides are weed killers. They're toxic. And unstable. Unstable to the point of entertainment. Now there is a part where when we teach the organic, the textbooks want us to use that as a nucleophile in SN2s. And I always I'm not writing that down. I'm skipping that. We're sticking with the hydroxides and the methoxides and the amides. But I'm not going to write the azides down. There is something you can do with it, but I don't think you should be using them. Here's what, I'm going to show you how to make them, and then how to gain entertainment from them. If we take some amide, we think of ammonia, which is NH3, and then reduce that to amide, and we take some nitrate, and we heat that. It has to be fairly strong, it's about 170 degrees Celsius there. You make the azide plus some hydroxide plus ammonia. Azides, not unlike carbon dioxide or N2O, linear. They're linear molecules. But one of the things that we're entering into trouble here is still on the board. No, not on the board. This needs to be lurking in your mind every time you deal things that contain nitrogen or contain nitrogen and oxygen. Nitrogen, N2, is 78% of the Earth's atmosphere. That's its most stable form. That's where it wants to be. So if we mess up, the chemical will revert to the form that it wants to be and go into the sky. So if I do something really, really dumb, here we go. This is lead azide. Lead azide is going to be a solid. And if this were lead azide, and I were to drop that lead azide, we would all be in huge trouble. Because it is shock sensitive. And you go back to making lead, and 3 moles of nitrogen gas. Okay. This is a solid. And obviously this is gas. All right, let's think for a second. Lead has an atomic mass of 207. Nitrogen has an atomic mass of 14. So 14, 14, 14, 30, 42, 84, 284, 291. So about 291 grams. That's quite a lot, actually. 291 grams of lead azide. And I dropped it, it would immediately make, what does 1 mole of gas, what volume what volume does 1 mole of any gas occupy? 22.4 liters. That's the molar volume, Avogadro told. So fix that. So this is now 67.2 liters. Oops. Now 1 mole of this gives me a mole of lead, which I don't need, and then 3 moles of gas, which is 67 grams. We use these as detonators. This is a detonator. And the trick is, anything that contains lots of nitrogen ultimately wants to go back into the sky. None of you were born, but you may have seen the video that Timothy McVeigh and Terry Nichols blew up a federal building, Murrah Federal Building in Oklahoma City, with the Ryder truck that just contained fertilizer. It contained ammonium nitrate. A few barrels of ammonium nitrate, nitrogen and oxygen, ammonium, nitrogen. And they just detonated it. Fertilizer like that explodes because it wants to go back to being nitrogen and oxygen. And so a container that contains a small confined number of moles that then has a large rapid expansion into gas, that's an explosion. Rapid evolutions of gas equals explosion. Okay? So beware. All right, let's look at ammonia. Ammonia is NH3, and we know it's got a lone pair of electrons. And that it is trigonal pyramid. What's the point group for a trigonal pyramid?
What's the what?
Point group. Yeah, it's see the stuff that we learned to be on one test isn't completely exclusive to that test. We now need to retain it. Here's the deal. Vertical axis is going to spin on that axis. And when this gets to here, it repeats. So what's that called? C3b. There's a spin axis that if you divide 360 by 3, you get 120 degrees. So a 120 degree rotation on its vertical axis gives you the molecule back. It is C3b. All right, so ammonia, I don't know how much just on its own. This is an incredibly important molecule. Where are you, ammonia? There's a thing, it's been around for a really long time at this point, called the Haber-Bosch process, where you take nitrogen gas and you take hydrogen gas, and that reaction is in equilibrium, and you make ammonia. And then ammonia is required as a fertilizer. This is done on the billions of tons scale. This is an enormous, enormous industrial application. We're looking at atmosphere pressures, about 150 atmospheres for this reaction to progress. We've got gases. I am not going to wait for those gases just to react with each other. Got to squeeze them together. I'm probably at this point, I'm certain it's been improved a little bit over the years, in the mid-hundreds of Celsius in order to make that reaction work. Think about the energy use this reaction is consuming. If an individual plant is making, I'm not getting millions of tons of fertilizer. This is a huge, huge thing. There is a global demand for that so that we can grow our crops faster and better. And the really sucky thing is that the yield on that reaction is in the 40s, 40%. Haber and Bosch, two Germans, one the industrialist. So Bosch did the high pressure, he built the high pressure factories, the plant to do this. And Fritz Haber was the mad scientist. He's the guy who, in World War I, decided instead of shelling the British and the French in their trenches, we should lob poison gas at them. Yeah, he's the original crazy nuts scientist. And after World War I, where he invented chemical weapons, he's the inventor of chemical weapons. He won the Nobel Prize. And then the Second World War came around, and he was useful there as well. To say that that's an iron catalyst is an understatement. It is really super complicated. But we'll stick with it. This massive, massive, massive waste of energy in order to get this. We are not getting nearly enough using this process, but it's what we've got for right now. Of course, nature doesn't make ammonia that way at all. Nature makes ammonia also, but it does it at room temperature or lower. I mean, it does it in the outside in the field with very little energy at all. And when we can mimic nature instead of trying to force the chemicals to react with each other, maybe we'll all get along a little bit better. So there is a thing, and it's called the nitrogen cycle. You may be aware that there is a carbon cycle. Biologists, have you learned the nitrogen cycle? Not enough to know that nitrogen and oxygen combine with lightning. Okay. So the book has a short way. It'll do. Where does my nitrogen appear? I have another little tiny book that I think does it better. I have a little rapid study guide. Okay. Here's your planet cells. I've ultimately got ammonia that is here. And nitrogen that is here. In combination with oxygen, I'm going to need a lightning bolt to make this happen. I'm going off script now because I don't really particularly like this. I'm not even going to write that I make NO2. Oh, this book says I should. Okay. I make NO2. And I make NO3. So nitrite and nitrate. And then there's a bunch of bacteria that will turn that nitrate back into nitrite, and then, oh, this is something we're going to have to deal with. There's lots of different types of combinations of nitrogens and oxygens. I think we'll get to that. We will get to that today. And these all siphon down into dinitrogen, which is then converted to ammonia. And this is where the trick is. And this is where I'll draw my little planet. In the roots, this is usually a legume. In the root system, you get little nodules. And those nodules contain one of two types of bacteria. Either Azotobacter or Pseudomonas. What have I got? Klebsiella. Pseudomonas klebsiella. Is that backwards? It's not Klebsiella, Pseudomonas, right? And Azotobacter vinelandiae. Wow. Okay. And what they do is just by using the natural energy resources that they pull from the plants, it's a symbiotic right here, they convert the nitrogen in the soil into ammonia. That ammonia fertilizes the plants, and the plant lives and prospers and reproduces, and the bacteria can now prosper itself. This is a little symbiosis. This right here is called fixation. The fixation is when you turn gas into something that is earthbound. So turning nitrogen into ammonia is nitrogen fixation. I did a PhD on nitrogen fixation. When I did it, I thought we would be close to a Nobel Prize and a breakthrough. It is now many years later, and nothing has changed. We still cannot figure it out. But when we do, oh boy, is that going to be a $1 trillion industry. This is the last obvious thing. How do I, because right now I'm using massive amounts of electricity and fossil fuel reserves, turning this unwilling molecule into that fertilizer. If I can just figure out how plants do it in the field at the low energy way, then I would be a billionaire. Hydrogen. So ammonia shows up in the nitrogen cycle, and there's nothing more important on the nitrogen cycle than ammonia. Other things not in the nitrogen cycle, well, not technically. It is actually in the pathway for nitrogen fixation, though, so it's not going to appear in your textbook. There is hydrazine, hydrazone 1 and 2 in the low pathway for nitrogen fixation, Thornley low. Hydrazine is NH2, NH2. Okay. That means those nitrogens are stuck together. It does still mean, though, that I have lone pairs of electrons. And you would never sketch those lone pairs of electrons being cis to one another. They're going to point away. They're going to point away from each other. They're occupying the most amount of space. And because this lone pair of electrons on that nitrogen is now attached to another electronegative atom, not as usable. basic than ammonia. The ammonia has got the H's pushing to it, and that's all. These each have nitrogen pulling away from them. And hydrazine can be made this way. Here's ammonia. And NaOCl. If we don't already know what NaOCl is, we should know. And we will know really soon. That's going to make NH2Cl and NaOH. And the NH2Cl is in turn going to react with another couple of ammonias to make N2H4, which is hydrazine, and NH4Cl. This is ammonia. And obviously this is base, sodium hydroxide. This is my hydrazine. And then this is ammonium chloride. And ammonium chloride is a soluble salt. All ammonium salts are soluble in water. Which then leads us to the question, what is NaOCl? What is that? This is a chemical it's called sodium hypochlorite. Sodium hypochlorite. You do all know this molecule by its trivial name. That's bleach. Okay. Are you all aware of whereabouts in your house you might find the bleach? Do you have bleach in your house? Okay. Are you all aware of where you might find the ammonia in your house? No. Windex. Glass cleaner. Cleaning supplies might use ammonia. Cleaning supplies might also use bleach. You do not mix these two worlds together, because when you mix these two worlds together, you make hydrazine. And what do we use hydrazine for? That's rocket fuel. I have never looked this up, but I bet you if we opened up YouTube, we can find videos of somebody blowing up their bathroom.
I use both.
If you pour your ammonium-based cleaning fluids into the same lavatory as your bleach-based cleaning fluids, you make rocket fuel. Keep those rolls apart. All right, so rocket fuel. Here we go. N2H4 plus some O2. Go tell me what you make. In order to have an explosion or a fire, you need three things: a source of ignition, a fuel, and oxygen. There's always oxygen. Oxygen is 21% of the Earth's atmosphere. There's always going to be oxygen. There's your rocket fuel. Just don't be the first person who smokes in the bathroom after your idiot cleaner puts bleach and Windex in the bathroom. Can you see what this wants to be? It wants to be a gas. Well, hydrogen is a liquid. A liquid. It's not unlike water. Its melting range, I think I've got it written down somewhere, is like 114 degrees Celsius, 3 degrees, what is it? 2. Its physical behavior mimics that of water. Can you see why? It's polar, protic. Has hydrogen bonding, just like water does. So it has about the same physical behavior. And then I've got 4 waters and 2 oxygens. This thing is going to blow up and make nitrogen and water. It's what the space shuttle uses. Not for the booster engines to leave orbit, but for the propulsion while it's in space and then on its descent back into Earth orbit. And kind of environment, well, not environmental friendly, but environmentally friendly. It just goes back to being nitrogen and water. All right, let's go make a big list of all of the things that nitrogen does in combination with oxygen. And this is going to be a big list. I'm going to do some molecules, but I'm also going to do another column of ions as well. So don't squeeze yourself completely out of page space right here. In terms of oxidation states, I've got everything from +1 to +5. +1, N2O, which is nitrous oxide, or more correctly, dinitrogen oxide. It is linear. And that length is 119 picometers. We don't need to know lengths, but there's going to be a point where we'll point at the molecules and go, look, that one's shorter. Look, that one's longer. You all know who Michael Faraday is? What's Michael Faraday's big contribution to civilization?
From physics, right?
He was either a physicist or a chemist, depending on which way you look at it, yeah. Okay. there's a Faraday cage which won't let any electromagnetic radiation in or out. So if you wanted, we used to have some instrumentation in the lab I worked in that was in a cage, so that outside radiation wouldn't impact the experiments that we were doing inside. But who invented electricity? It's not, I was going to say, it's not on the board. I was like looking at the board, hinting to the board, but it's on the board. It's not on the board. Michael Faraday. Michael Faraday is the guy that put a coil of wire around a moving magnet and moved the electrons in the wire. He's the father of electricity, this guy. Batteries existed before him, but that was direct current. And it was a chemical means. And then, Americans unfortunately think that Benjamin Franklin invented electricity by flying a kite with a key on it, and it probably never even happened. And we don't generate any of our electricity supply by flying kites in lightning storms. So, nice story. No truth in it at all, none. Michael Faraday. Now, Michael Faraday was the protege of another huge scientist called Sir Humphrey Davy. Sir Humphrey Davy took Michael Faraday in as an apprentice when he was a teenager. And Sir Humphrey Davy was this distinguished scientist. And Michael Faraday was a bit of a lad. And Michael Faraday, I don't think he invented nitrous oxide, but he was a user of nitrous oxide, because nitrous oxide is also called that's laughing gas. The dentists use it now to put you into kind of a drunken state when they drill your teeth. Kind of takes the edge off. There are tales of Michael Faraday showing up to the Royal Society to give a lecture completely out of his mind because he'd been to a laughing gas party. +2. Nitrogen monoxide or nitric oxide. What else do we use nitrous oxide for? Anything? Anything? Anything at all? Street racing? You ever watch The Fast and the Furious? Proud to say I haven't. My son loves those movies. But a little bleed of nitrous oxide into the fuel system of your engine ups the explosiveness, because again you're making nitrogen. You're making nitrogen and oxygen. Nitric oxide has to be linear, of course, because it's just an N and an O, and its bond is a little bit shorter. Little bit. It is colorless. And it has something useful. It is paramagnetic. Paramagnetism is that very weak magnetism that we see molecules display when they have unpaired electrons. There is a loose electron in nitric oxide. Okay. In the very early 90s, I was looking around for something to do, for an interesting molecule, and thinking, well, maybe when I become a professor, I'll go look at that, because that's kind of interesting. And then this came across my radar, nitric oxide. And it has an unpaired electron. It's got an electron that doesn't belong to either of those atoms, and I thought that's kind of interesting. And then, I think it's like 1992, 93, it got voted International Molecule of the Year, which is kind of strange, because people had finally solved its electronic structure. And then, out of nowhere, it became a billion-dollar molecule, overnight. Do we know what NO does? It's a vasodilator. It improves blood flow. And it was originally developed as a drug for, I believe, heart disease. Pfizer, it was Pfizer. I was going to say Upjohn. Pfizer developed a drug to improve blood flow, probably for patients who had heart disease. And it had a rather profound side effect. That drug was called Viagra, because that improves blood flow. And like, bam, billion-dollar drug. N2O3, dinitrogen trioxide, is a very strange little molecule. It is planar. Planarity tells us there is something much more complicated going on in this molecule than you would think, because that should be turning, and it isn't. And this is a blue liquid. The blue color is also a giveaway that there are electrons moving between low pairs of electrons and pi bonds, probably. There is something going on in this molecule that is not revealed by its structure. This is going to be kind of strange. And this makes NO and NO2. It's going to fall apart. Wouldn't expect this to be yet. Okay. At +4, I might run out of real estate. At +4, I have NO2, which is just nitrogen dioxide. What's my angle here? Angle's 134, and the bond length is 119. Well, that 134 is not 120, so there's something potentially missing from this diagram, and that is brown and paramagnetic. And is in equilibrium with N2O4. If we get a second, we'll come back and we'll look at all of the Lewis. We'll draw some of the Lewis structures for this, and this is colorless. And this equilibrium is colorless liquid. Ooh, hello. Wave your hands back. It's not a power outage. Why would the light go out? You all sat so still. Seriously? There you go. This is an equilibrium. If I put N2O4 as a liquid inside a little flask, and I warm it up with my hands, because its melting point is 11 degrees. I think is it 11 or negative 11? Negative 11. I warm it up with my hands, it turns into the gas, it dissociates, and the flask goes brown, and then I don't touch it, and it goes back to being removed. And then at +5, I have N2O5 dinitrogen pentoxide. There's no way that nitrogen has enough electrons to handle everything that's going on here. Some of these are covalent bonds and some of them are dative coordinate covalent bonds. Let's get through the list and maybe we'll come back and revisit. Because I took up a bit of space here with that. I'm going to put my ions here now. Under the +1, I have hyponitrite, which is N2O2, 2 minus. That is O, N, N, O, all with the 2 minus. Under the +2, I have nitrite. Hypo, in a word, means less than, underneath. This is NO2 minus. Here I've got a nitrogen, just like, where am I? Like a nitrogen dioxide, but now with a negative charge. And if I compare, these bond lengths are now 124, and the angle is 115. So the bond got to be longer. At 3 plus, I have NO plus, which is called nitrosonium. And it's just an N and an O plus here. This is something that we are going to come back and visit. This word, this phrase does not mean anything to you yet. That's a pi acid. Pi acids are going to appear much later. I'm going to skip over 4, and we're going to hit 5. And at 5, I have nitrates, which is NO3 minus. And I have nitronium, which is NO2 plus. And in the nitrate, each of those oxygens takes it in turns being negative. 122 picometer bonds. And in the nitronium, have much, much shorter bonds. We don't have time to talk about that because we're out. But maybe what we should do at some point is figure out this nitrogen has a lone pair of electrons and 1, 2, 3 electrons. How can it possibly get away with doing this? That one of those bonds is a coordinate covalent bond to an oxygen and the other is a Okay. We'll do nitrogen, maybe it's just a tiny bit more. Some oxygen. A little bit of sulfur, a little bit of tellurium. I think we know pretty much everything we need to know about the halogens. The interhalogens are in general chemistry, although they're mostly skipped. And then we'll hit the transition metals next week.